We are going to start talking about ray tracing acceleration and the use of acceleration structures, starting with the use of grids. First, let's discuss the use of acceleration in a ray tracing. Testing each object for each ray is very slow. You need to test the number of objects for each of the number of pixels. Therefore, over the years, a number of alternative approaches have been proposed that make ray tracing faster. One of these is to have fewer rays. That can involve methods like adaptive sampling and depth control. Alternatively, one can consider rays that can intersect with multiple pixels or multiple objects simultaneously, and this led to the development of techniques such as beam tracing, pencil tracing, and cone tracing. What we are most interested in is ways in which we can have fewer numbers of intersections. One approach in which to do this and make the intersections faster is to optimize ray object intersections. There are very efficient methods, especially for intersecting rays with triangles, that can be heavily optimized. Still another approach is to use fewer intersections. In fact, that will be the main focus of this lecture. We refer to this as using a ray tracing acceleration structure. Every modern ray tracer must have an acceleration structure. When I talk about acceleration structure, I mean a conventional ray tracing acceleration structure, such as a grid that we're going to be talking about now, or perhaps a bounding volume hierarchy. In fact, for homework 1 on the ray tracer, you are required to do an acceleration structure, and it will be very important for the rest of the course because the ray tracer can be very slow without an acceleration structure. One of the simplest acceleration structures is a bounding box. These bounding boxes can possibly be hierarchical, and we will refer to them as the bounding volume hierarchy later. As you can see in this example, you have a number of triangles which are covered within this volume of this rectangular box, which is known as the bounding box. We do not need to intersect the ray with each triangle. In fact, if a ray misses the bounding box entirely, then we can stop the tests right there, and we don't need to intersect with each triangle. Extensions of this idea involve also spatial hierarchies such as octrees, KD trees, and BSP trees, which we'll talk about briefly later in the lecture. We will start in this segment of the lecture talking about uniform spatial subdivision or grids. In the next segment, we'll talk about bounding volume hierarchies. After that, we'll talk about binary space partitioning or BSP trees. When these binary space partitioning trees are aligned with the axes, we will refer to them as axis-aligned KD trees. The acceleration structures that we will study in this course are conceptually simple. However, implementation is somewhat tricky. This lecture is at a high level, and likely if you actually implement them, you will need to work out details, and you may need to look at other references for that, or you can work out the details yourself. I do want to stress again that having an acceleration structure is critical to achieve reasonable speeds and reasonable performance. For those of you who are developing in NVIDIA optics instead of simply writing it yourself in software, there is a built-in bounding volume hierarchy structure. So you do not really need to do anything, but the additional difficulty of getting it working in optics compensates. And in this case, you are welcome to just directly use the optics bounding volume hierarchy structure. The first acceleration structure we will discuss is the regular grid. In this example, I am showing a scene which has a few circles or ellipses in it, and it has a grid on it. In this case, it is a regular grid. The ray is traversing the grid, And we can go from grid cell to grid cell. So the ray starts at the first grid cell. That grid cell is empty, it doesn't have any geometry. So the ray moves to the next grid cell, and so on. Finally, we get to a grid cell that actually has geometry. You notice that ellipse here intersects a number of different grid cells, including the one we are currently at. It needs to be associated with each of those grid cells, needs to have a list of geometry, in this case the ellipse. Therefore, we need to test the ray against this circle or ellipse. Since the ray misses, we move on to the next grid cell, where we again test the same object because that object covers multiple grid cells. In practice, we can use a technique, for example, known as mailboxing, where if we had tested an object once at an earlier grid cell and found that it misses, then we do not need to repeat the test. We continue along this way. Again, here we need to test against this object. And again, the ray misses, so we continue until finally we hit this grid cell and the ray does in fact intersect the object. One of the interesting things that I want to say is that this object, there was actually an intersection test done. And similarly, if you look at this object, there was an intersection test that was run on this object. However, if you consider this object or this object here, there is no test that was run on these objects. Okay. Therefore, we have only intersected two of the four objects. I've given you a brief overview of acceleration structure known as the regular grid. This is the simplest acceleration structure, and if you want to simplify your life, I highly recommend that you just implement a regular grid. For example, a 5 by 5 by 5 grid. And in fact, there have been softwares over the past that have been widely used that have used only this acceleration structure. One challenge is that you can have triangles or other geometry that overlaps multiple grid cells. You need to store that geometry associated with each grid cell that it overlaps. As I showed in my toy example on the previous slide, you march along the grid. You need to be careful with this. We'll talk about it a little bit on the next slide. You test against each triangle in the grid cell. More sophisticated options of the regular grid are things like KD trees, octrees, or BSP trees. We'll talk a little bit about BSP trees later in the lecture. Alternatively, you can use hierarchical bounding boxes or bounding volume hierarchies, which will be the second segment of this lecture. We will close out this segment by talking about the traversal of the grid. I will note that this is really a very high-level discussion, and you will need to actually think about the practical implementation. Conceptually, it's straightforward. I just showed you the way in which you go through the different grid cells. However, one challenge is that, let's say I start here with this grid cell. How do I know which is the next grid cell, and at what location do I enter the next grid cell? In this case, the next grid cell is here. Now, you might think that the algorithm would immediately go to this grid cell next. But in fact, what we end up doing is going to this grid cell in the Y direction and then again in the X direction. After that, we do the intersection. So how does this work? We can think about the algorithm in terms of two parallel plane intersections. If I just draw the vertical lines, then the intersection is actually quite simple. If you have a particular intersection point, let's say this point is x0, y0, and this distance is known, it's just equal to delta x. We also know the slope at which y0 is moving, so that this distance will be known as delta y. And then it is easy to consider the intersections. For example, this intersection point will be x0 plus 2 delta x and y0 minus 2 delta y. So this is a very regular grid structure. Similarly, if we consider the horizontal lines themselves, then again the point is moving in a very regular pattern and you can find these intersections. The challenge here is that you are considering grid intersections along both the vertical grid lines and the horizontal grid lines. The way in which you handle that is you sort the intersections. Therefore, you sort the distances for the intersections along the vertical grid lines, which are regular, and then the horizontal grid lines, which are also regular. And each time you pick up the intersection that is closer, and you keep both of these lists every time picking the intersection point that is closer. And in this way, you can traverse the grid and you can extend it from 2D to 3D.